I want to introduce you to our historical figure for the week. This is Doug Englebart, who ran the mother of all demos, which was a really, really important demonstration of the potential future of technology. He was, among other things, the inventor of the computer mouse, one of the progenitors of the GUI, the graphical user interface, and led to a revolution in the way that people and computers interact. He was, in many ways, the first person to engage in study of human-computer interaction. That's one of the many fields that's available to study as a researcher or as a developer within computer science, and it essentially asks the question of what way can we best design computers to meet human needs when we're interacting with them on an ongoing basis. So that includes things like the study of VR, user interface design, how people interact in terms of their emotions with a computer. All those elements of the more social side of computer science are captured in human-computer interaction, the field that was pioneered by Doug Englebart. Among his less notable honors is that he was the grandfather of my childhood best friend, whom I married in kindergarten. That is a fact that you will not find on the internet anywhere else.
Okay, there's Don Andrews' hand in Menlo Park. And in a second we'll see the screen that he's working and the way the tracking spot moves in conjunction with movements of that mouse. I don't know why we call it a mouse. Sometimes I apologize. It started that way and we never did change it. In its first form in about a year, and ended up sometime later with some 20 experimental computers in a network, which would be enough so that I could be running a system in Cambridge over the network and getting the same kind of response on a CRT.
Moving on to some frustrations that you might have been having interacting with your own computers, C, as you will have noticed thus far, does not have a string type. Now, this has proven pretty unfortunate for us as we've had to deal with individual characters. However, it's not such a leap to go from where you might be now, where you're dealing with characters, to go from where you might want to be for your assignment, which is, of course, dealing with strings. Now, what is the connection between strings and characters? There should be something pretty obvious. A string is made up of characters. So if we can find some way of grouping our characters together and delineating when a group of characters forms a word or a string or a sentence or anything like that, we can effectively use the tools that we already have within our programming language in order to build a more powerful and more effective system for interacting with strings, which are much more common in ordinary life than just characters. So in C, we could do this with just a series of characters in memory. And what we do to ease the way in which we use them is to add a sentinel value, that is a null byte or a byte that has the value of 0 to the end of our series of characters to mark out when this group of characters ends. Why do we do this funny sentinel thing? Why do we add a null byte in the end? Why don't we just specify how long the string is? To have a sentinel at the end of the array allows us to leave out the argument when we're using functions of how long the string is. So when you've been dealing with arrays and on your mid-semester test, every time you used an array, you had to specify to a function that was using it how long the array was. But when we're dealing with strings, that's probably too much of an annoyance for us. Much better if we can let the computer figure out where the string ends. And we do this by marking the end of it off with a null byte, with a character. Now, there's definitely a performance trade-off with this because you can't know ahead of time where a string ends. But given that most strings that we tend to use in ordinary life are fairly short, this might be a trade-off that we're happy to do. If you're not happy with this trade-off, there's nothing to stop you from going ahead and making your own version of a string, just having an array of characters, and instead of having a null byte at the end, you could instead pass along with the array every time you use it the length of the array, and write your own string functions and so on and so forth. But it's awfully convenient to have a type that contains this null byte at the end, so we don't have to do that and can use a lot of the built-in work that the computer's done for us. So strings in C are really a form of syntactic sugar, just like arrays were syntactic sugar in that they were an easy way to write something that we could have done using more complicated syntax. We could have used pointers and never had arrays in the first place. Strings are the same kind of thing. It's just like using pointers. It's just like using arrays, only this time we're going to specify ahead of time that it is going to be a set of characters that can either be stored in a typical array or just stored in memory and accessed via a pointer, and then we have a null byte at the end. The special thing is that C is going to provide syntax through a number of library functions that allow us to avoid thinking about the array all the time and thinking about the pointer all the time. In order to use most of the functions to do with strings in C, you have to use one of these two headers, and the lighting in here is not helpful, so maybe we'll switch to AV and give us a few spots, if that works. No, that makes things worse. Okay, we'll just leave it at that and leave Liam to deal with the low light situation. The battery's dead? Yeah. Anyway, so if you include those two headers, you get access to this wide array of different functions. Now, I went in the man pages and extracted all of these for you. You, of course, do not need to know them all, but knowing how to find them is quite useful. So if you just Google manpage string.h and ctype.h, you can get all these different functions that allow you to handle strings. For the purposes of the assignment, some of these will be more useful and less useful, as well as in everyday coding. But it's worth getting familiar with at least some of the important ones. Particularly, we'll look at functions such as strlen, strlen, which gets you the length of a string. And given what we've discussed so far, knowing that a string is just a series of characters in an array or in memory ended by a null byte, you should be able to write that one very quickly. Another one that we will use, or that you will use frequently, is strcpy, string copy, that copies a string from one of the arguments into the other argument, and along with a whole bunch of character functions which allow us to deal with individual characters and determine things about their properties without having to refer back to the ASCII table. So for example, isLower is a function that when given a character tells you if the character is lowercase or uppercase. This is particularly useful to when dealing with the English alphabet in ASCII, so you don't have to remember, is my character between like 65 and 110, I think it might be, for uppercase, or between 110 and 140 for lowercase, whatever the numbers happen to be. You don't have to remember it anymore. You can just use this function from ctype.h. We also have things that allow you to tell whether a character is alphanumeric, whether it's a digit, etc., etc. Encourage you to go and at least skim some of these and get familiar with the tools that might be available to you. Obviously, there's not enough time in this class to cover every single possible string function or character function, and so as part of your maturation as programmers, developers, and computer scientists, you're going to have to start learning to discover these things for yourself, either by Googling, looking on Stack Overflow, or by reading the manual. This now brings us to a series of demos. The actual learning part of strings that we had to do now with new material was very, very short. We're already at the point where you can do pretty much anything that there is to be done with strings. It's just a matter of taking the skills you've already learned and applying them. So we'll bring up our demos for the day. And why is, oh, wrong button. There we go. Demos for the day, and we will start with string 1. This is a fairly simple demo. I'm not even going to run it first because the code is nice and simple. All this is going to do is it's going to create a string using one form of string initialization syntax that you see right there on line 7. And then it's just going to loop through and show the change in address as you access each different point in the string. So the string in this case has 3, 6, 7, 8, 9, 10, 11 characters. The amount of memory that we need to hold it is of size 12 because, of course, there is a null byte at the end. And we're going to loop through each of these different possible indices using a pointer and print out the address at each point and the string at each point. So to print out the address, we'll use a %p, which you've seen before with pointers. And then to print out the string, we're going to use a new format specifier, %s. If we run it, when we access the first element of the string, the first character, the first position in the string, we get the full string. We then increment the pointer by 1, and we're now accessing the next memory address. If we were to imagine that our string is just taking a view of the computer's memory, if we start at the very beginning of the string, we of course will see the full string. But if we move along and start only at the address after the first character, we'll still see a string. It's still a sequence of characters, and it's still terminated by a null byte. However, this time, because we've moved one along, we no longer have a view of that very first character. And so instead of seeing the whole string printed, Cheshire, smiley, we now just see Heshire. And as we increment our pointer, our address moves along by another byte, and we see an increasingly smaller suffix of the string. Now, suffixes are going to become pretty important when we start doing string search, and in particular, one of the string search algorithms that we care about is reliant on this idea of suffixes. So knowing ahead of time that you can generate a suffix of a string simply by changing the point in the string at which you begin your accesses is an important concept that we'll come back to. Do we have any questions on strings so far, just to make sure we're all tracking? Nope. Good on strings? Okay, let's move on to our next demo. This demo is strcpy. strcpy is, as advertised, it is a function to copy a string from one argument into the other argument. There are going to be a few features of this program that might seem a little interesting to you. So the first is that we're going to define our destination string using a really large character array. Why might we be doing this? Why is our destination string going to be really big? Liam, can I have the... Why do we have our destination string as pretty large? And tell me what your name is. Hold the microphone up.
My name is Jamal.
You'll have to send that in an email to me after. It's going to be difficult for me to get the first time. Why do you think the character string for our destination is so large? Well, what do you think? Do we know ahead of time what size string we're going to be copying in? So what if we're reading in a text file, and the text file has really long words, and we're going to be putting each word into its own string, and we copy it from one place to another? Do we know ahead of time how large those words are going to be? Yeah, so you might want to have space for a really large string, and because we don't yet know how to dynamically give ourselves more memory, we're going to have to, at the very beginning, when we start doing this whole process, give ourselves a lot of room for things in which to put our string. What might go wrong with this? What happens if I have a really, really long string? Will the program work?
No.
Why won't it work? Yeah, so we've only got space for 1,000 characters. So if you give me a string that's more than 1,000 characters, that's probably not going to work. Do you have a guess to what might happen? Would we get an error? Or what happens when you use too much memory that doesn't belong to you? It starts with an S, seg. Get a seg fault. Remember, this is what happened if we started pushing into memory that wasn't allocated ahead of time. Now, of course, it's not a guarantee. We might get lucky, and it might just be the case that even though we've exceeded the amount of memory that we allocated for our string, there just happens to be a space in the memory there that isn't being used for anything important that we can cut into a little bit. However, if we start going too far past it, eventually we're going to hit some memory that is sensitive, that contains maybe the return address of where we want to go when we finish the function, and we'll get a seg fault. So this is one thing to be very careful with strings, is they're a very common source of not only errors with programs, but security flaws with programs. Now, for the time being, we don't necessarily expect your program to be perfectly secure, but it's worth knowing ahead of time to start building in ways to think about your program such that when we do eventually get to dynamic memory allocation, this isn't a trap into which you fall. So we've set aside a chunk of 1,000 chars in memory, so that's 1,000 slots for potential characters. What's the maximum size of a string that we could fit in here? And just put your hand up, and I'm not going to run the microphone. Yeah? Could we actually fit a string of 1,000 characters in there? What do we have at the end of every string? We could fit 999 characters, of course, because we need to save one character at the end for a null byte. This is another common source of off by one errors in string programming, is forgetting to make room for the null byte, or forgetting that the null byte is there, or if you're writing your own string function, forgetting to put the null byte in at the end. So we have two different versions of our strcopy function, string copy 1 and string copy 2. The reason we've done this is just to show you two different ways of writing the same function. One other thing to note here with our string copy function, and this is not in the downloaded code, but I've added a special specifier here, the word const, before char source here. So we're going to have our source string and our destination, but there's something special. I'm using the word const here to indicate that the source string, as an argument, it should not be modified by the string copy function. We don't want the string copy function to ruin our original string in any way. We want it to make a clean new copy. Now, of course, because it's referring to memory, because it's a pointer or an array, whichever way you look at it, it's possible for the string copy function to modify the source string, but we don't want to allow it to do this. In fact, it's even better if the compiler gives us an error if we try and modify it, and that lets us know that we're making a mistake. So to signal to the compiler that inside strcopy, it shouldn't allow us to modify the source, we can add the word const. And this will ensure or help the compiler to know that we shouldn't be modifying it and to throw an error if we do. And that'll help us again with our coding and help point out errors. It's part of the type definition. Exactly what role it plays in C syntax is outside scope, but it is a modifier to the type. We have a typical while loop here. We just initialize our counter variable, and we're going to be checking at each stage, are we at the end of the string? And we will do this on the iPad in a moment, once I've set us up with a sample string. At each stage, we want to check whether we're at the end of the string. The way we do that is by checking to see, is the current byte, is the current character that we're looking at a null byte or not? The only place in a string that a null byte is allowed to occur is at the very end. And this is okay because a null byte doesn't actually refer to any normal character that you'd see in a string. It's not the same as a character 0. So you could imagine writing a 0 out and that would fit in like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But those are ASCII values as well as integer values. The ASCII value for the character 0 is not the same as the number 0. And we'll look at this shortly with our demo and see what happens if we get it to look for that instead of that. This is a null byte with a slash out the front. That is just the character 0. And so we reserve this special null byte as an indication of a character that is not useful in any other way other than to signal the end of the string. Assuming we're not at the end of the string, the way that we can copy one string from another is just by keeping track of where in the destination and where in the source we are, and moving along, copying one at a time the characters over. At each stage, once we've copied it over, we then move to the next character. And remember, at the very end of your copy, to add the null byte into your destination. And you don't add the null byte into the last possible index. So if we go back up, we had space for 1,000 letters, but we don't put the null byte at the end of the 1,000 letters. Why don't we do that? Remind me your name?
Steven.
Steven, yeah. So why don't we put the null byte at the end of the 1,000 characters?
Because the indexing is to 999.
So that would even though we have room for 999 normal characters, the 1,000th spot is reserved for the null byte in that one if we have a string of 999 characters. But when we use string copy, do we know that we have a string of 999 characters? No. So where do we put the null byte in instead? So if I have the string hi, the null byte goes after which letter?
I.
Goes after the I at the end of our string. and I is not 999 letters. How many letters is high? 2. So we put the null byte at position, well, 2 in the 2 by array indices, and it's the 3rd position. So yes, that was a confusing question. So if we're looking at that more generally, if we have a string that's n characters long, at which position do we put the null byte?
N+1.
Yeah, and well, n in the array and the nth plus 1 location. So this is why instead of placing the null byte at the very end of the array that we made room for a string, that array is only if we get a string that's really, really large. But most of our strings are going to be smaller, and so what we do is we put the null byte at the end of the letters that we've copied. So if we'd copied the letters hi, after we've done the hi, then we put the null byte at the end of those. This is another potential error to trip you up. To remember to put the null byte not only at the end, but at the right end. You want to put it at the end of the characters that you're using, not at the end of the memory that you've allocated.
Sam Shepard has a really nice comment.
I'm not going to be able to get to it easily, I don't think. Let me see. You can put it up here. Sam Shepard says, learning about the null byte reminds me of learning in primary school that you end every sentence with a full stop. That's actually a pretty good way of understanding it. You can have saved a whole page in your diary for letters, and you could put your full stop at the very end of the page, but that would make no sense. You put your full stop at the end of the words that you've put in, not at the end of the page, even though you've given yourself more room to write. Thank you very much, Sam, for that. Neo asks, what if we add extra characters into the array? Will the null byte be shifting 1 index backwards? So the answer to that is if you're in charge of adding characters into the array, then you're also going to be in charge of deciding where to put the null byte. So if you want to extend the string hi, null byte, into the string hi space there, you will have to change the position of the null byte yourself. So you could say that, let's call the string m. Positions 0 and 1 would be hi, and then position 2 would be the null byte. If you want to change that into hi there, you would now change position 2 into a space, position 3 into t, position 4 into h, etc., etc. And you'd also have to remember to, at the end of the there, to put the null byte in its new location. So if you are the one that is writing the string function, you are in charge of putting the null byte in the right place. And again, if you forget to do this, or you mess it up, or you leave the null byte out, you're going to run into trouble. Is null byte false? The null byte is equal to 0, and so it behaves the same way that a 0 would in anywhere else in your program. And that is 0 integer value, not 0 character. Again, another source of confusion with strings that you might run into. Remember to differentiate between the character 0 and a null byte, which is equivalent to the integer 0. Because we're in ASCII, integer 0 and character 0 are not the same thing. So now I think we're just about ready to run our program once. And we can see that we have copied test1 into str, and then we've printed str, and the contents of it are test1. Now we're about to reuse it. We're going to reuse our string str, and that's okay because it's just a location in memory. We can copy new things into it. And we're going to copy in test2. Only this time we're going to use a different strcopy function. Let's take a look at this one. Wow, that's some pretty short code there. In fact, this is quite a nice and elegant way of writing it that relies not only on the fact that strings are really just pointing to memory addresses, which are pointers, but it also relies on the fact that you can do pointer arithmetic and that we have a very tightly constructed order of operations in C. So let's start off by making our pointer equal to the location where we want to be putting things in our new string. Of course, if we create a pointer p and we point it at destination, and destination is a chunk of memory, this is at the first location in destination in which we could place something. This is the same as writing the address of destination 0. Now what we have here is a very tight loop with nothing inside. You'll notice nothing there, just a semicolon to end the loop. So this is where all the work is being done. Let's break it down into a few pieces. So first, what is our loop termination condition? Our loop termination condition is when the thing inside the parentheses equals to 0. When does it equal to 0? When whatever this is equal to 0. Because remember, the result of an assignment is the value that was assigned. So if the value that we're assigning from source into P is 0, if this is 0, then the value of this parenthetical is also 0. So this while loop is going to run until there's a 0 on that side. Next, what happens is we store the result of dereferencing source into the result of dereferencing P by order of operations. So we copy whatever value is in source into P, and remember P starts off as the first location in our destination. And then what we do is we do pointer arithmetic to move to the next location in the destination and also increase the pointer source by 1. Yeah, why are we returning the destination address? It's not strictly necessary. It doesn't make this particular program run any better. However, imagine that you wanted to do, let's say we're writing a function string cat that adds to, that puts concatenate, that concatenates source 1 and source 2 and puts them in destination. Now let's say we want to chain this together and add the result of this to another string. I could call string cat des2, source 3, and this would concatenate string 1 to string 2 and then string 2 to string 3. And the only reason we can do this is because this returns a pointer to what it produced at the end, and so this allows us to use it as an argument in other functions. It's just a bit of syntactical nicety. It doesn't actually change the overall behavior of the programs themselves. Make sense? Okay, I think that covers us for string copy, more or less. Let me see if there are any other features in here that I wanted to point out. Yeah, one other point that I've missed here is we have a special form of strings that we're using here. These are constant strings. They're not variables. It's like writing the number 5 in the code. 5 is not a variable, it's a constant value. And you can do that for strings as well. You can use a string, and the compiler once again is doing some cleverness here. It will store this value inside the program's code, and then it will allow you to use it as an argument. There's another way of declaring a string like this, and you could do so now we have created another constant string in the code, but I haven't used the word constant here. This is another source of potential traps. Despite the fact that I'm not saying constant, when you declare a string in this way, the compiler automatically treats it as memory that you can't alter. Why does it do this? Well, think back to our discussion on segments. This actually gets stored in one of the segments belonging to program data and not on the stack. So this isn't a variable that you can use like any other. The pointer is on the stack, but the memory that it's pointing to is inside one of the protected segments. So if you try and modify it, you'll actually get a segfault because you're accessing part of the program's memory that isn't available for variables. This is being used up by constant values, such as storing the number 5 somewhere in your code, or more likely the number 55,000, and static variables and string constants like that. And I think that now covers us for our string copy function. Let's look at getWord.c. One thing you'll note about this particular source file is that it doesn't have a main function. So let's see what happens if I compile it. I'm getting an error. The compiler is asking for a main function because a main function is always where C programs start from, but the linker can't find it. Now this would be okay if I'd given it 2 different C files in there, if I'd given it getWord.c and main.c, if main.c had a main function, the linker would know that, okay, there's nothing, I don't start inside getWord.c, I start in main.c. That's where the main function is. And the linker, remember, combines your different bits of your program together. But because there's no main function, the linker can't find it. If you look at the error message, it says implicit entry start for main executable. That means we're asking the compiler to imply where to start, but there is no place that it can find. It can't find a main function, and so it can't make this jump on our behalf of where to actually start the program running. But we can use this as a way to store functions that we want to combine with other programs. So as we'll see in many of our coming demos, we can use one file, write some code in it, and combine it with another file that has a main function in order to allow us to reuse some of the code that we're going to use frequently across a number of different programs. Now, what does this little function do? Well, we've got our comment here that helpfully tells us. If we have standard input that the user is typing in, it is going to separate the input out into words. Now, this should be a very easy crowd question, so if you want a chocolate and haven't had a chance yet, also grab a chocolate for Stephen. Let's see if I can get this out there. Pretty good. Are you chocolate as well? Nope, that one missed. Go grab it. So the question for this was, how do we delineate in user input between different words? Or even on sentences on a page, words on a page, how do I tell the difference between where one word starts and another word starts? This is a really easy one. Space. Okay, Henny, you got it.
Space.
There you go.
Thank you.
Yeah, so the way we tell whether we are at the start, you know what, we're going to borrow that for a little longer, is if there is a space. However, not all new words start with a space before them. What might an exception to that be? Can you think of a place on a page of a book where a word starts and there isn't a space before?
A new line character?
Yeah, so if we're on a new line of a book, like think of a physical book and we get to a new line, we don't have to read past a space in order to get to the first word on the line. So we have another condition. The first is if it's preceded by a space or if it starts on a new line. Are there any other instances that we should think about?
End of file.
End of file would be another case where we should know to delineate against. This isn't necessarily where we'll find a new word, but it is something that we should be aware of. So I think we've covered all the major problem points. And now all we have to do is write a program that detects when we've just seen a space and when we've just seen a new line. And if we've just seen a new line, then we're not looking for a space anymore. Let's take a glance at the program that does this. We are allowing our program in this case to take as input the destination for the word. I'm going to call that W. And as well, to get around the problem of running into seg faults because we haven't saved enough memory, we're going to keep track of the maximum word size that we're allowing in this program. We will eventually, when we see malloc, get past having to have these limits, but for the time being, it's an important part of your code. We are going to create an integer here, and this could be a character. We're going to create an integer here to store our character. And we're going to use another function that I think we might have seen in this class before, but if you haven't, it's getChar. And if we open up in our terminal and ask for what getChar is, get next character or word from input stream. So getChar doesn't take any arguments, and getChar is equivalent to getC. And what does getC do? It acts equivalently to fgetC, but as a macro. Okay, what does this do? fgetC, the function obtains the next input character from the stream pointed at by stream, or the next character pushed back to the stream. Yeah, we're not going to talk about what streams are, thank you, Liam. But all you need to know is that it's going to get the next character from stdin, standard in, which is the input stream where all characters come from when a user types on the keyboard. And then if these are successful, these routines return the next requested object from the stream. That means it's going to give us the next character that's present on the stream. So parsing all of that into something a little more understandable, if we call getChar, it'll just give us the next character that it hasn't yet read in. So if we're not at the end of the file, thank you, Henny, and if the character is not an alphanumeric character, skip it. But we do this in a loop. We want to pass over all punctuation characters because it's not just spaces that are not part of words, it's also full stops, it's exclamation marks, etc., etc. So by having this in a loop, it's keep reading characters until you get a character that is part of the alphabet. I said alphanumeric before, I meant alphabetical. If the thing that you read in was an end of file character, and we know this by the special value EOF, return EOF from the function. So pass this value back to the function that called getWord. Okay, if we have now skipped past all the punctuation preceding, and we're now at the start of the word, put inside len, which is going to be a counter variable that counts how long our word is, put at the len index of the word the character that we just read, and then do our increment. So what this allows us to do is increases the value of length by 1 after it's finished everything else on the line, which allows us to save one line. What we could do to make this a little bit more readable is we could do that, and it would be the same, but by C's order of operations, this allows us to, at the same time, store the character at the current index and also increment the index so that we know how many characters we've read so far. We also want to do a check to make sure that we haven't read in so many letters that we're over the limit or at the limit. The way we do this is by checking after every time we read in to make sure that we are strictly less than the limit. And then we can do this again, because now we've found the start of the word, we keep reading until we're at the end of the word. So you'll notice a distinction between this little segment here and that little segment here, is that there is a not next to the alpha. So now we want to keep reading in letters while they are alphabetical and stop when they're not or when we reach the end of file. When we're done reading in letters, remember to set the null byte at the end of it and then return. And in this case, we're just returning 0 if we have successfully read in a word. One could also imagine changing the function prototype to return len so that the calling function knows how long the length is. Or if we wanted to do what string copy was doing, you could even return the pointer to the word so that you could use it in that kind of nested syntax. So that takes us to words.c. And you'll see at the top of this file, I'm including word.c. What this means is that the preprocessor, the part of the compiler that runs before the compilation actually happens, is going to copy into the program everything from getWord.c. So let's compile that and just see that happen. And this is called words.c. Now we don't get a linker error, and because we've got a main function, and we're able to use getWord even though nowhere in this file is the getWord function. We only have a prototype at the top here. Now what would happen if I move this down to the bottom? Will it still work? It still works even though we use getWord over here because we have a prototype up the top, and then the preprocessor runs and adds in the main body of the code down below. Or at least you can think of it that way. Another thing that you might do is include a header file, which includes a whole lot of function prototypes, and then rely on the compiler to search a bunch of locations that it already knows about for the actual C files. So we're not including string.c here, we're including string.h, which only includes the function prototypes. However, because the string library is a really core part of the C programming language, our compiler comes built in with a list of places on the computer to search for the .c files, or for the pre-compiled versions of the .c files that it can add in and mash together. We could just as easily do the same thing for our getWord function and move our prototype, getWord, into the .h file. And that starts to allow us to decompose our single very large program file into a more understandable and more reasonable program structure that allows us to reuse code in efficient ways rather than having it all in one giant file. Now, unfortunately, thanks to our infrastructure, you're unable to do this for assignment 1. For assignment 1, please keep all your code to a single file, but hopefully for future projects, we will enable you to use multiple files and to organize your code in a way that makes logical sense. So we have a couple minutes left, and we will take a quick look at getWord. We've now declared a new type, a word T type, and our word T type is a type def for a character array of max chars plus 1. So now we're being clever and explicitly saying that we're going to allow the word to be 1,000, it's going to be 10 characters long with 1 extra space left over for the null byte. So this will allow us to have as many characters as max chars in there. We're also going to set a maximum to how many words this program is going to read in. And what we want to do with this program is to find how many distinct words there are and their locations at which they appear in a given input. The given input might either be a large file or it might just be you typing in standard in. We're going to reuse our getWord file, and at the end of every getWord, we're going to check if we've hit the end of file yet. The arguments to getWord are going to be our one word, the place that we're going to put our new word in, and our limit, which is max chars. So that's going to be reused in word.c like we saw before. We're also going to have a counter for how many distinct words we've seen and how many total words we've seen, and then move on from there. So every time we get a new word, we're going to increment the count of how many words we've seen total. We're going to set a flag that determines whether we have found a word we're looking for yet. And what word are we going to check if we've found? We're going to see if the word we've just read in is the same as any of the prior words that we've read in before. This is essentially what a distinct word is. It's a word that exists nowhere in our collection of words that we've already seen. This is a linear search through an array of all the words. Of all the words that we've already read in, sorry. If the word isn't found, and we are below the number of max words, our limit for the number of words, copy our new word that we just read into all words, which is our collection of distinct words. And then increment the number of distinct words by 1. At the end of that, once we're out of the loop, so once we've either read too many words or we've hit the end of file, print out how many words total we read in, and then print out how many distinct words that there are, and print each of those words. Let's give this a run, and then we are done for the day. So there were 5 words total. Hi there, you. That's 5. But there are only 3 different words. Hi there, you. Now, we didn't actually need to do them all on a new line because, of course, we are removing all non-alphabetical characters. There you go. Still works. Now let's test it on one last input. You can see we've processed the entire text of Moby Dick and found all the distinct words in their order of appearance. With that, we are done with our string demos for today. We'll have one more demo tomorrow, and then we'll move into one of the trickiest algorithms for the semester, the KMP pattern search algorithm. And we'll learn some new concepts that will enable us to take this fairly tricky algorithm and break it down into some smaller pieces. Thank you very much. I'll catch you all tomorrow.